Thank you very much for inviting me here and for being here. The first time I came to St. Petersburg, it was in 92 or 93, I don't remember exactly. It was for a conference dedicated to A.D. Alexandrov and Boozman. The topic I will talk today about is related to the work of Boozman and Alexandrov. Of course, at that time, I was not so much interested in the works of Alexandrov and Boozman. I was interested to come and see St. Petersburg. It was the first time I come to Russia, but then gradually I became more involved in this metric geometry, and probably more importantly than metric geometry, I learned from reading Alexandrov and Boozman that the important things are the very simple things, in fact, in mathematics. The ideas are eventually basic Euclidean geometry and things like this. This is the topic which I will talk about today. So it's metric geometry, and I like this because it makes. I mean, I came to this because I was interested in the metric geometry of Teichmüller space, especially Thurston's metric, which is a non-symmetric metric. So I became interested in non-symmetric metrics, and I wanted to have examples of non-symmetric metrics to see what are the problems that arise. And progressively, I worked. I mean, on this topic. It became a second topic for me. So I would, let me mention that I have in my work on this, the last years, I have two collaborators. This was Mark Troyanov and Sumio Yamada. So different. We have no paper together, the three of us. It's different works. So let me start with an example. So this is an example of a non-symmetric metric. This is what we call the semi-Apollonian metric. So we have a convex set omega in Euclidean space, and then we want to define the distance between 2 points, x and y. So the convex set may be bounded or unbounded, and then we define the distance as the the logarithm of the supremum of the Euclidean distance from x to a divided by y to a. So these are Euclidean distances, and the supremum is over a in the boundary of omega. So this is kind of a metric. When I speak about a metric, I mean a an object which satisfies the axioms of the metric space except the symmetry. The distance from x to y is not necessarily equal to the distance from y to x. In all my talk today. So you have such a metric, and then you ask the usual questions. I mean, the questions which you ask in Euclidean geometry. If you want, you can take a special omega or a circle, and then you ask what are the propositions in Euclid's elements which hold for this metric. So you need a notion of triangle in this metric. In order to study properties of triangles, you need that's it. But I mean, in fact, we know better than Euclid. Now we want you want to introduce the notion of geodesic. So a geodesic in this very general setting. So this is a map, say from an interval into your space, such that the distance between gamma A1 and gamma A3 is equal to the distance between gamma A1, gamma A2, plus distance between gamma A2, gamma A3,
A1, A2.
For every A1, A2, A3 in that order in this interval.
There is a misprint in the second one.
Okay. A1, A3, A1, A2. Yes. A1, gamma A2. Thank you. Okay, so you have geodesics, and the first question is you want to identify geodesics. So what can you say? What are the geodesics in this metric? It turns out that I don't know the answer in the general case, but one result is that if omega is a disk, interior of a circle, then the circles orthogonal to the boundary are geodesics. So it resembles a little in this sense the Poincaré metric of the unit disk, and it's not difficult to see, in fact, that when omega is a disk, then the arithmetic symmetrization of D, that is D symmetrized of xy equals 1/2 D of xy plus D of yx. This is in fact the Poincaré metric disk. So this metric, semi-Apollonian metric, is kind of half of the hyperbolic metric, and well, the same thing holds for the well, upper half plane. This is more or less everything. This example is the only interesting example on this metric where I can say something significant. Probably not because it's too difficult, but because I didn't spend a lot of time. Didn't spend enough time on this, and from here you see you have a wealth of metric spaces of various shapes, which I think are interesting to study. So Piotr said that I'm teaching a course on Teichmüller theory, and I want to mention a metric here, which is Vintner metric on Teichmüller space. I'm not going to define Teichmüller space now. I will talk about this in my course, but I just want to mention the definition and to see the analogy, to show the analogy with this definition here. So the Vintner metric on Teichmüller space, it's a metric between metric spaces. In fact, it's a metric between hyperbolic metrics. We have a surface, say, of genus 2, and then we have two hyperbolic metrics, G1, G2, and then I want to define a distance between them, and the distance, in fact, this is the Thurston distance. Well, it is log of sup. So here I have a fraction, and I have x and y, but it's. I could put G1 above and G2 below. It would give also something interesting, but let me give it in the right way. Where the supremum gamma, well, gamma is, you see, gamma is closed geodesics. Gamma is closed geodesics, and this is the length of the closed geodesic gamma for the metric G2 divided by the length of the closed geodesic gamma for the metric G1. And you see in Thurston's theory, when you know that there's a space of geodesics which is situated on the boundary of Teichmüller space, then I'm taking here the logarithm of the supremum of some functions on the boundary, and then the analogy becomes clear. The analogy becomes clear with this metric, and here, although this example is much more sophisticated, you know, that the one there, then here we can say a lot about this metric. We can say a lot about its geodesics. We can say a lot about its curvature, about all the, I mean, a lot of interesting features. Its boundary structure. So here also you have boundary structure. You can talk about boundary structure. You have whatever if you want to study. You see the distance from a point, from this formula, the distance from a point to the boundary, which I see here, is infinite. Is infinite. When I have a sequence of points going to infinity, when y goes to infinity, then the distance from x to y, the distance from x to y becomes infinite, because the distance from y to some point here on the boundary becomes small, so this becomes infinite. And so you have also the notion of boundary, and so on. So this is one aspect of this analogy. You know, we as mathematicians we work on analogies. In fact, we try to guess what we want to prove. Yes. Sorry.
Should we somehow normalize the metrics? Because if like just
hyperbolic metrics.
Okay.
These are just metrics of constant curvature. But it's true that you can vary. Of constant equal curvature. But constant curvature equals to -1. But it's true that you have variations of this. I mean, you can study metrics, which you can define distance between metric. I mean, the thing about you need hyperbolic metrics. Well, even now, I mean, from hyperbolic geometry, this is the length of a closed geodesic is always positive, and there's a unique geodesic which realizes this length. And here, in Thurston's theory, you see it's not only gamma. Gamma is a dense subset of a certain set of objects which are more general than the geodesics, and this set here is this is called projective measured laminations, and this is a compact set. And when you take the supremum over some compact set, then you know that you have something which attains the supremum. This is very important in this theory. Here the boundary could be compact or non-compact, in fact. And okay, so whatever. This was my initial motivation to study this kind of metrics. And by the way, when you have non-symmetric metrics like this one, I told you that in one special case, the symmetrization is interesting. I mean, it's something familiar. Here, you have this non-symmetric metrics on Teichmüller space. Of course, you can symmetrize. You can symmetrize using this formula, but nothing remains from Thurston's theory. I mean, here there's a beautiful theory, a beautiful development on the geodesics, on the Finsler structure, on the I mean, on the relations with the rest of all the other all the rest of Thurston's theory on surfaces. If you symmetrize, then you lose everything, in fact, which is also an indication of the fact that non-symmetric metrics sometimes are more interesting than the standard ones.
And what is this symmetrization? I mean,
yeah, well, you can symmetrize. In fact, you can symmetrize by taking. You define the symmetrization. You can define this symmetrization, taking the arithmetic mean. But and then you want to prove theorems about this.
But for Taylor's space, for Thurston's metric.
This is what I'm saying. I mean, you can define it, but then you don't have any interesting result on it. You have many results on the non-symmetric version. You symmetrize, and then you lose all these results. You are in an unknown world when you symmetrize here. I mean, your question is, okay, what is the symmetrization? I don't know. I know how to define it, but I don't know anything interesting about it. And by the way, you see, you can symmetrize in different ways here. Here, for instance, well, you can take the maximum. You can take the maximum instead of the and I don't know what happens to the maximum metric here in this case of the Poincaré disk. If you symmetrize, you lose the Poincaré disk, of course, and I don't know any interesting property of this metric. And here for Thurston's metric, again, you have different sorts of symmetrizations. On some of them, there are infinitesimal results, like on this one, the max symmetrization, but not the one I erased. Okay, so I want to talk now about another non-symmetric metric on convex sets. So again, I have a convex set. So by the way, Teichmüller space, we want it to behave like a convex set. I mean, we think of it as a convex set, but it's not, in fact, in any sense of the word. It's not a convex set, but it has the properties of convex sets. Like people also want to think about it as a symmetric space. It's not at all a symmetric space, but it has all, I mean, most of the beautiful properties of symmetric spaces and so on. So anyway, so this is another metric now on convex sets, and this is called the Funk metric. And the definition is also very simple. So here I take 2 points, x and y. I suppose they are distinct. If they are not distinct, then the distance is 0. If they are distinct, then, well, I join x to y by a Euclidean line. It hits the boundary at a point B, and I define, let's call it f for Funk, f of x, y as, again, I'm using Euclidean distance from x to b divided by the distance from y to b. And, well, I have a metric. Here, in the previous case, it was more or less clear that the metric satisfies the triangle inequality. Here,
should take the logarithm here.
You are right. Yes, thank you. I should take the logarithm. I always forget logarithm. So even with the logarithm, it's not clear that, I mean, it's not straightforward that it satisfies the triangle inequality. You see, you have 3 points, x, y, and v, and then to compare the distance from x to y to the distance from x to z, and the distance from y, from z to y, you have to take into account 3 points, you see, and then you have to deal with these 6 points. And but in fact, there is a geometric proof that this satisfies the triangle inequality. In fact, you can copy the same proof for the Hilbert metric the triangle inequality for the Hilbert metric is something which is contained in an appendix. I mean, it has to be proved also. I mean, it's not trivial. It's contained in the appendix of the later versions of Hilbert's Foundations of Geometry. He has an appendix on where he proves the triangle inequality. It uses the Menelaus theorem, you know, the Euclidean Menelaus theorem, because you have triangle with 3 other points and so on. Anyway, so this is the Funk metric. And then again, you can ask all the good problems. I mean, at least for some specific convex sets. The fact that it's planar or non-planar, I don't think it plays any role in fact, but specific convex sets, meaning whether it's polyhedral or not, or smooth boundary and so on. So this is interesting. In fact, there are interesting properties. Let me say a few obvious properties here. One obvious property is that here, in fact, for any convex set omega, the Euclidean lines are geodesic for this metric, and this I said is obvious, you see, because I take a Euclidean line, then I take 3 points x, y, and z, and I want to show that the triangle inequality is an equality, in fact, to show that this is a geodesic. But then, well, to compute the distance from x to y, I need this point b. From y to z, I need the same point b. From x to z, I need the same point b, and so on. And then it's a question of ratios, and the logarithm transforms the multiplication into an addition, and I get that this Euclidean line is a geodesic. So this is easy here. It's also easy to see that the Euclidean lines are the only geodesics if and only if boundary omega is strictly convex. Let me just make a picture for this. You see, if the boundary is not strictly convex, so suppose the boundary contains some Euclidean line like this, then when you take x, then let's take a point y here and a point z here, and then look at this line. You see the distance from x to y is this divided by this, which is also equal to, well, this divided by this, and the distance from y to z again is this divided by this, and the distance from x to z is this divided by this. This is just Euclidean, the Euclidean intercept theorem, and so again with the logarithm, the multiplication becomes an addition. So the distance from x to y plus the distance from y to z is equal to the distance from x to z. And not only for these 3 points, but if I take any triple of points on this broken line, I have exactly the same reasoning and the same result, which shows that this broken line, in fact, is a geodesic. This broken line is a geodesic. And in fact, if I have, by the same reasoning, if I have something, a straight line in the boundary, then any curve, in fact, any curve which is monotonous like this is geodesic. And then you have all sorts of questions about the geodesics. So take a triangle. If you like symmetry, you can take a equilateral triangle, and then the question is, take any two points in this space and describe the convex hull of the geodesics joining. Describe all the geodesics. Say something interesting about all the geodesics which join these points. And then if you know the answer for this, if you find the answer for the triangle, you can take more complicated figures and then say something interesting about polygons. And then you see, in this kind of, when you work in this kind of theory, then there are results. I mean, the known results are of two kinds: either polyhedra or smooth and strictly convex. This is the general philosophy when you work on these things. So anyway, so you have this kind of, and then you can ask after geodesics, you can ask questions about circles. Let me just mention a result about circles. I will take again the example of a triangle, but the result is general here. The result is general. So I take a point. Let's say this one here. A point. Let's call it again x. And I want to describe the set of points which are at equal distance from x. This is I take a certain radius, and I want to describe the circle of radius r around x. So I do this. Suppose this is distance r here, and then I want to describe the other points, the rest of the points. So notice first that if you take a parallel here, if you take a parallel to this side, then by the same reasoning that I erased the similar Euclidean triangles, you see these, all the points on this line here are at the same distance. You see, this divided by this is equal to this divided by this, and so on. So this line here belongs to my circle centered at x, and then at some point my reasoning after some point my reasoning fails because I cannot continue here when I arrive to this point here. So this line here is in my this Euclidean segment is in my circle, but then here I have to continue the other parallel to the other side. Okay, and the same here, I have to continue parallel to the other side, and now I have a geometric proof that this must close here. This must close anyway. And then I find something which I hope is general for any convex set omega, not only for triangles. I find the fact that my circle is well, it's homothetic to the entire convex set. This is true. The special case I did here is a general fact. In fact, it's a general proposition that in this func geometry, if I draw a small circle around me at points at equal distance, then I see the boundary. I have a picture of the boundary of my set, which is at infinity. In fact, the distance from a point here to the boundary is infinite. And this is interesting because it implies, this is kind of a rigidity result which tells me that if two func metrics are, if I have a local isometry, in fact, any local isometry from a point here, any local isometry between some open set here and an open set here for the func metrics implies that the shapes must be the same. The boundary must, since I see the shape around me. In fact, you can make this more precise. The local geometry implies the global geometry. So this is one property of the func metric. Now the func metric is interesting. In fact, by the way, there's I mentioned an analogy between this semi-Apollonian metric and a metric on Teichmüller space. And I mentioned the name Yamada at the beginning of my lecture. So Yamada defined a func-like metric also on Teichmüller space. So I explained to him this kind of thing. And then you see, you have all these metrics, I mean these two metrics at least, you have the underlying Euclidean metric, and you are using the underlying Euclidean metric to define a new metric. So you can generalize this to several settings. In fact, and Yamada had something called the he called it the func Weil-Petersen metric, where he used the Weil-Petersen metric on Teichmüller space and its structure at infinity, and the fact that when you hit from a point here, a point at infinity, the length is finite. The length is finite when you do it correctly, in fact. Then you take 2 points in Teichmüller space, x and y, and you have the boundary at infinity is kind of something, the Weil-Petersen boundary, and then you define the same, and he developed this kind of func Weil-Petersen metric. Anyway, this is good, and this is also an indication that you have a lot of I mean, between this very simple construction here in Euclidean geometry and the complicated construction that uses the Weil-Petersen theory of Teichmüller space, I'm sure you have a lot of intermediate examples. Anyway, now I want to discuss something about the Finsler geometry. the Finsler geometry of this Funk metric. So Piotr told me I have only 1 hour, so I have to watch the time. Finsler geometry is, you see, when you have a metric like this one, or like this one, or like the Thurston metric, we have 3 metrics now which we know. A natural question is to see whether it comes from an infinitesimal norm. That is, you see, when you have, let me just remind you of something very simple. In fact, you have, when you have, you see, you have a here you have a manifold, say, equipped with a metric, and this metric gives you the distance between 2 points. It allows you to know the distance between 2 points, and the question is whether you want to. The question is whether this metric comes from a norm on tangent spaces. You want to know whether this metric can be defined by minimizing the lengths of curves that join these 2 points. And then how do you measure lengths of curves, in fact? Well, this is where the infinitesimal thing comes into play. So suppose you have on each tangent space a norm. In this case here, it will be a norm, but non-symmetric norm. So it satisfies all the axioms of a norm except the symmetry axiom. The norm of x is not necessarily equal to the norm of minus x. This is very natural in this setting where we are looking at metrics where the distance from x to y is not necessarily equal to the distance from y to x. This is the only thing that goes wrong, this non-symmetry. Anyway, so we are asking whether this metric comes from an infinitesimal norm, that is, whether we have a family of norms on our tangent bundle, such that, well, a norm on each tangent space, such that when I take a gamma, say this is, let's call it omega again, and here I need gamma to be piecewise C1. Although I mentioned Busemann, he hated the differentiability. He doesn't. I mean, this point of view of doing mathematics, you want to do everything without differentiable structures, but you can do it, but then it's very complicated. But suppose we have differentiable structure, then you have on the tangent space we have norms, and then for a piecewise C1 gamma, for each tangent vector, we know its norm, right? So in this case, I can integrate my set of I can integrate my norms along this curve gamma and define the length of gamma, and then my metric is Finsler if it is equal to such a metric here. Now, you see, there are metrics which are Finsler metrics. There are metrics which are non-Finsler metrics. Let me mention that the Thurston metric, which I defined, is a Finsler metric. If you symmetrize it using this this formula here of the formula I gave of half of the sum, then I don't know if the result is a Vintner metric. This is the kind of questions which I said I don't know any good result. So there's a general result which tells you that if you have a Vintner metric, if you take them, if I take the maximmetrization for the Thurston metric, then I don't know whether it is Vintner or not. If I take the arithmetic symmetrization, then there's a general result which tells me that it is Vintner. But anyway, so I want to give another version of this Vintner structure on a manifold. You see, instead of talking about norms on tangent space, I want to forget the norm and just keep the unit ball of the norm. This is better because because of my talk, because I'm talking about convex sets, and the unit ball is a convex set. And here I can see a Vintner manifold. In fact, I can see a Vintner manifold just as a parametrized family of convex sets. In each, so I have a manifold, and in each tangent space I have a convex set, which is it comes from the norm, in fact, but I forget the norm. I just keep the convex set, and so and it gives me all I want, because this convex set in the tangent space tells me what are the vectors of norm 1, and then for the other vectors I can just intersect with this unit ball and see the norm of my vector. So I'm saying this because this Funk metric, defined like this, in fact, is always a Vintner metric, and in fact, the unit ball, the convex set which I told you about, the unit ball is in fact omega itself. Is omega itself centered at the point. You see, it's not like the norms on vector space where you are translating the same ball. Here it's very different, because let me show this again on a. Well, maybe the best thing is to do it with the unit circle. So here, so I'm talking about the Funk metric. The Funk metric on this unit disk. At the center of the disk, the ball is round and symmetric around the origin. This is the set itself. But here, at a point here, you see the unit ball is round, but it's not centered at that point. So at each point, the unit ball is the set itself, but with a different center. And this is, I mean, this is, of course, because it cannot be the same. It cannot be the same everywhere. So this is why this Funk metric, in fact, because of this property, the Funk metric, we called it the tautological Vintner metric, because at each point the convex set defining my Vintner structure is the set itself. Now the Funk metric is related to another metric, which should be familiar to more people. This is the Hilbert metric. The Hilbert metric of omega. The Hilbert metric of omega is just the symmetrization h of xy is 1/2 of f of xy plus f of yx. This is usually written in terms of the cross ratio. The cross ratio, if you have x and y, and then the Hilbert distance, you have to do this divided by this plus this divided by this, and you obtain exactly the cross ratio, in fact. And then when you know, you see, in my experience, the things are much clearer. Many things you can prove them much more easily for the Funk metric than the Hilbert metric. And then a few things, they remain when you take this. When you do this symmetrization, then a few important things remain. For instance, when I said that for the Funk metric, the Euclidean lines are geodesics, then obviously when you do this, the Euclidean lines will be also geodesics. The reason is that Euclidean line, it's Euclidean in this sense, and it's also Euclidean in the other sense. If a Euclidean line is Euclidean in this sense, and this is very different from the Thurston metric, where geodesics for his metric in one direction are not geodesics in the other direction. And this makes things much more complicated for the symmetrization. So here you have easily the fact that for the Hilbert metric you have this property. And then the next question is there are many questions which you can ask, but one is about the Vintner structure of the Hilbert metric. I showed, in fact, I didn't show you, but I told you that for the Funk metric, the convex set is the set itself. By the way, when I symmetrize the Funk metric of the unit disk, I find another model of hyperbolic geometry. You remember we had this Poincaré model when we symmetrize the semi-Apollonian metric. Here, if I symmetrize the Funk metric of the disk, I find what is called the Cayley or the Cayley-Beltrami or the Cayley-Beltrami and then somebody else also model of Cayley-Klein-Beltrami model of hyperbolic geometry. So we have something again, something familiar. I mean, this just tells you that okay, I have all these. You see all these Funk metrics associated to these convex sets, or this one here, or this one here, and so on. One of them, I can say something interesting. Then I know something about the symmetrization. But there are all these others. In fact, millions of these convex sets, which gives rise to Funk metrics and Hilbert metrics, which are all interesting to study. You see, you can study shapes of. I said something about circles. You can study shapes of triangles. You can study properties of triangles for these metrics. For instance, ask whether what are the Funk metrics where the three altitudes meet in one point. For instance, you see, I know that this is true for the hyperbolic metric, which is not obvious at all. In fact, it needs a proof that the three altitudes in a triangle or the three medians also meet in a point. For the Funk metric or for the Hilbert metric, I don't know. In fact, I don't know because I never took enough time to investigate this type of questions. But you have millions of spaces which are interesting, I think, to study. Maybe I have to finish in 1 minute, but I wanted to say something about the Finsler structure of the Hilbert metric. So again, we have a set omega. We have a set omega, and then at some point, in fact, as I said, we know that the Hilbert metric is Finsler because it's a arithmetic symmetrization of a Finsler metric, and this you can prove that it's Finsler. And then you want to find the shape of the convex set. We already said that a Finsler structure is a family of convex sets. So at this point, I have a convex set attached, and then there's a nice algorithm here. It should be symmetric. You know, it should be symmetric because I know that the Hilbert metric is symmetric. And this is, I mean, you cannot guess the answer because the theory of symmetrization of convex sets is a complicated theory, and there are many symmetrizations, and none is better than the other. And then you have to invent a new symmetrization, and this symmetrization is, I like it because it makes again use of this this called I forgot. There are three means in Greek geometry: the arithmetic, the geometric mean, and then the third one, harmonic mean. Yeah, harmonic mean. It makes use of this harmonic mean, and it's like this. So okay, I take a point here. And I want to find the convex set, the symmetric convex set. Then I look at a section. I look at the intersection of a line with my convex set, and I find a segment. This is the segment, and this is I have two lengths, A and B. Two Euclidean lengths, A and B, which in general are different. And then I have this harmonic mean 1 over m equals 1 over a plus 1 over b. Probably there's 1/2 somewhere. So I find this m, and I replace this segment by a new segment symmetric around x, and where the radius is m. And I do this for all these sections, for all the intersections of omega with lines passing through x, and I take the union and I find my symmetric set. This is the construction of the Vintner structure of this of the Hilbert metric. So I think I have to stop here.
Let's thank the speaker. Other questions or remarks?
Yes.
I have a question about the first example, the semi-Apollonian one.
Yes.
Is it a geodesic metric? You mentioned that you don't know what is a geodesic.
Yes.
Are there geodesics there?
Yeah, you are right. I don't know. I don't know. Probably it is, but I don't know. Yeah. Yeah.
Well, I have a guess.
Yes.
It's complicated.
Uh-huh. Uh-huh. Uh-huh.
There should be some near the boundary, but they could kind of end up in the interior and not extend further. That's my guess.
Okay. Yeah, okay. Okay. Okay.
Other questions?
Yes.
Is there any natural sequence of Riemannian metrics approximating, say, Thurston metric?
Yeah, I never thought about this. This is a very good question.
The
thing is that I don't track the Riemannian things. You know, you're asking me a question. I want to avoid Riemannian, but this is. Are there? Yeah, I think the answer should be yes. Maybe by general. You see, there's a description of the. Thurston describes the unit ball of this metric at each point as an embedding of the space of measured laminations as a convex set, and this convex set. I mean, I don't know. I mean, the thing, the most obvious thing, which is probably not interesting. I want to approximate this convex set by a sequence of. I'm not sure you can approximate it by a sequence of round balls. I'm not sure, but it's maybe. I mean, in this special case, maybe it seems. I mean, it seems you can. I don't know. I don't know. The answer is I don't know. But I think it's interesting. Yeah.
More questions? So let's thank the speaker again.